So welcome back. We have 2 hours until lunch, so I hope not to take you that time, to take all the time. But I really want to start, given we've been talking about the quantum repeaters from the various different levels, I kind of want to start talking about networks and the internet, okay? And I want to make a distinction now that we have a huge confusion in our community, okay? The internet is a network of networks. I see so many people using the quantum internet and showing a picture or saying, here's a simple network. But the internet is a heterogeneous series of networks that are connected together. And so that we are a very, very long way from the quantum internet, or even what it looks like. But we are making exceptionally good progress on moving towards quantum networks. So just to bring back up one of the slides we had, so basically, I use this in the first lecture to say QKD, the test beds that are around the world, and I've put a few of these up there, but we've seen remarkable progress over the last 20 years, maybe more. I forget now when the Boston network actually started, okay? I know I was involved with SECO-QC when I lived in Europe. And I mean, these kind of demonstrations that were done were designed to take us beyond a point-to-point link and start to show us a little bit about how networks would operate with multi-parties. So one that I was very familiar with was, of course, being an NTT, was the Tokyo QKD network, which ran for many years. I think it's still operational at the moment. And there, as a network, we had a slight problem for many years, okay? At certain times of the day, the network would just drop out. Nothing's changed on the two endpoints, but we're suddenly going from getting good key rate to suddenly no key rate, okay? Why? It took them years to find it, but the problem is in Japan, we hang fibers on telephone poles. You get the breeze the right way. We add enough noise, the key rate generates. 20 minutes, half an hour later, the breeze subsides and comes in a different direction, the key comes back. So it teaches you lots and lots of things. So basically, QKD, in terms of these testbed networks, many countries have them. They're teaching us a lot about how the components of those networks operate, and it's also forcing us as a community to interface between the quantum people and the telecom people. So we're putting stuff into their racks and various things like this, so we've got to understand actually how they do things. But I mean, I do want to get to a planetary network. I have been thinking crazy ideas recently about, okay, how do I do communication, quantum communication to the moon or Mars? And various things like this to go beyond this. But I mean, networking is enough that I can't highlight all the kind of work. This is just one out of doubt from a few years ago with Diamond. We've got the teleportation stuff coming from Wolfgang Tittle's group. I mean, there are many kind of pioneering experiments where we're starting to learn a lot about this, okay? We do need to kind of think about a kind of roadmap. How do we move from where we are today to the future? I mean, I'm not going to be able to build a quantum internet just from scratch. And I mean, I'm probably old enough to frighten you, most of you, by saying, when I started in the networking field, we did not use Cat5 cable. or even Cat1 cable. In my early days of computing, we were running RS232 cable between buildings, okay? Which is very high loss cabling, various things like this, but we kind of need to think, how do we build up? And as part of this building, make sure that these small scale test beds that we're building are versatile to cover a number of applications. So I will talk a bit more at the end about quantum edge computing and various things like this. But if we really want to think about what we're going to do on quantum networks, obviously QKD. I said earlier on, QKD is, I don't need it for networks as a special application, but it is an application. I mean, once I can distribute entangled resources, I can use this for QKD. I can also use this, if it's multi-party entanglement, for conference key agreement and various things like this. So there are cryptographic primitives to this. We saw from Arthur and various things talking about certain other applications where there are cryptographic protocols that we will use. Probably one of the big ones is distributed quantum computation, okay? And that's one of the really, really hard ones. Quantum computation is hard. Adding photons to it just makes it 10 times harder. But then we've got things like quantum enhanced sensing, clock synchronization. There's a whole series of these. So in a sense, what are our core challenges? Entanglement distribution over distance, reliable quantum memories. And you notice I put question marks for this. Do I need them or not? That's a decision that I know I'm probably going to need entanglement distribution, I think. Do I need memories? Actually, practically, I'll say yes. I don't see a choice. We need them. But all photonic repeaters don't have memories. So it is optional in a sense. Synchronization timing. So one of the things is that as you start thinking about distributing entanglement, I may not want memories, but do I need buffers? Do I need a way of resynchronizing? Do I need to take this photon pulse that's coming in now and slow it down for a nanosecond? A nanosecond this time, a minute later, it's 100 picoseconds. And these buffers are normally something that we tend to forget about, okay? But it's something that's important. Error correction at scale. Yeah. And we will need interoperability and standards. Why? Because one, the internet will be a network of networks. We'll be taking appliances from these things are going to have to talk to one another at the moment, okay? At what level that is a different question, okay? It may be that I have a box manufacturer A here, generates this entanglement, it comes out into some third-party thing, is then converted to do something else. But where we do this, how do you do interoperability at the moment? In the computing area, we're reasonably interoperable. In quantum communications, we've got to think about it. So that's kind of the core challenges going forward that I see, or some of them. And standards, I mean, I know we've had a talk in this thing about standards. I still have the personal concern that for QKD, standards are necessary now. If I don't know the form of the hardware or what its functionality is or how it's going to operate, do I need the standards absolutely now? I need to start thinking about it, but you just have to be careful that the standards follow what's going to happen in a sense. Because standards also have the habit of forcing the community along a path. Once there's a standard, you tend not to move too far off that standard. So if we standardize now and we want to do something different, there are headaches. Quantum networks. I really like linear networks. I really, really like linear networks, okay? I don't have to think about routing. I don't have to think about who my neighbors are. It's very simple in a sense, okay? You send me something, I pass it. But when I start thinking about arbitrary networks where there's bottlenecks, I have to start thinking about how I route information, how the priorities are. And then as we get to bigger networks, okay, well, what did I say this was? This was a snapshot of some of the nodes of the quantum internet, I think in about 97. And what I have on here is I have Alice as a point here. I have Bob as a point here. And these are all connected lines. Please tell me the path between Alice and Bob. Yeah. Okay. And whatever path I showed you now, that may not be the path that's being used in 5 minutes' time. Because paths change, okay, depending on the circumstances. So we have to get to the stage with the linear network, Alice and Bob, they need to know nothing else. But in here, when we get to large-scale networks, Alice and Bob will not know the path between the two of them. The network is going to have to sort that out. And we've seen this diagram many, many times, okay? The OSI model, okay, for networking, where you go from the physical layer through the data links and network, transport, session, presentation, application. That's the classical case. This is going to have to move across into the quantum world, okay? In the quantum world, things may not be as easy. We could use it, but I may not have the distinct gaps between all the layers that we've tried to maintain in the classical world. And just to kind of show you at the moment where things go, our bits kind of at the physical layer. So these are our single photon polarization qubits. Our packets are kind of sit here, and then we kind of come up. But problems in quantum mechanically, we may inadvertently mix these things together. So we really have to be careful. But typically what you want, and that's one thing that's important about the model, the application layer, you should not have to know what's going on down here to get your application to work, okay? The whole reason we have these models is so that we can abstract stuff away. As a distributed quantum algorithms designer, I don't want to know what TCP/IP does. I want to be able to just come from the highest layer and say, okay, I just put a network call, I just call this API or whatever it is, and it goes away and does it all for me, and I can forget about it. So I mean, I'm not going to talk down here at the physical layer, okay? I want to step up and to start thinking about the networks themselves. Luckily, I used to work for NTT in Japan, okay, for over a decade. And the nice word we have in our title is telegraph, okay? Telephone and telegraph. So one of the things that we have to think about when you think about networking, how am I sending this information? I mean, and the simplest way, and in some ways the oldest way, is the concept of the circuit switch networking. Before you and I want to communicate, we establish a circuit, then you and I have a circuit, and then we can just talk as long as we want. But while you and I are talking, you can't talk to me. Once I've finished, we release that circuit and we do the next case. So circuit switch networks are important. They're still used today. You may think no one uses circuit switch networks. There are applications where we still want them, okay? The problem though is resources. Just some of the key characteristics that I just flashed up there in a sense, okay? So the circuit switch network, dedicated link, exclusive, okay? We can't have a circuit switch network that shares between us three, in a sense, easily. Some of the key characteristics, okay? You must establish the circuit before you start transmitting data. It's a dedicated path while we're talking. So while you and I are talking, the way that we talk never changes. It's not like I can suddenly go directly and then go around and come back. That's not the concept behind circuit switch networks. And then after we finish talking, we have to tear the cord down. So at the moment, we don't, I mean, in the early days of quantum communication, we're very likely to be using circuit switch networking.
Is there even a way to get rid of them?
Yes.
How?
we did not set this up in advance, okay? So I'm saying for convenience, the circuit switch networking, it's the easiest way to go about. So we can think about packet switch networking, okay? And people like Cisco had been doing a lot of work on actually trying to create quantum packets where this kind of stuff is working. It's hard because actually having, and I'll come back to this in a second, but let me just run through this. So the key in a packet switch network is the route is not predefined. So this first packet goes this way, the second packet goes, this way, the third packet goes this way. In the circuit switch network, I send you packet 1, packet 2, or I send you block information 1, block information 2, block information 3. You receive 1, 2, 3. When I do packets, when I do packets, 3, 6, 1, 12, they all arrive out of order, and you have to resynchronize them to get the right order. But the advantage that you have is that you can then use many different paths. This path selection is not fixed. So just some of the characteristics of packet switch networking, the key ones here, data split into packets, the small chunks, okay? Typically we have the data, we have a header which has information about where I'm sending it to, IP, maybe routing information, and then there's a trailer that has some other information in it. I can talk to people afterwards about this. Dynamic routing, typically each packet can take a different path. Typically once there's a good path, it doesn't change that much, but it can do if you get someone evil like me who decides to come through and cut the fiber one by one. You have to reassemble the message from the packets at the other end. So if you and I want to do video over circuit switch network, I can just ship you raw video, okay? And it should work. If you and I want to do video, we have to do some buffering because you have to reassemble things to be able to watch the movie. packet switch networkings are much more efficient in terms of resources. You and I may be holding a circuit switch channel open and we send one message a day, okay? The rest of the time, it's completely wasted. If you and I are not talking, I can talk to other people. You can talk to other people. So really, do I want circuit switching? Do I want packet switching? Okay. And I'm just going to slowly come to this in terms of the repeaters, okay? It's my belief, and I'm not, there are ways around it. If you're using first generation repeaters, okay, you are probably going to be circuit switched. I just don't, it just seems too big a headache, too complicated to do it otherwise. The second and third generation repeaters could use packet switching potentially. They could also use circuit switching. But I think if you had many people on a network wanting to send quantum data around, you're going to want to use this network efficiently. So therefore, packet switching is going to come in. There's some early work a while ago from colleagues at Cisco who were trying to create data packets, quantum data packets, with both the classical and the quantum information sitting within one packet, okay? This is challenging to get quantum and classical to coexist, even in the same fiber. The QKD communities had huge challenges with this because what else is in that channel at the same time? Well, what's in the fiber next to it at the same time can have big impact. So I'm saying this stuff is not easy, but people have been starting to think about the concepts of quantum packets and various things like this. So if it's quantum, one of the things I could think about in terms of the header, yes, that's the destination I want to get to. Maybe it's the IP address. What could be in the trailer? If I'm using error correction, maybe the poorly framed information is part of the trailer. Not a simple problem, but it's something people are starting to think about. Routing. And we had a very nice talk yesterday. So do you want to use static routing? Do you want to use dynamic routing? Do you want to use traditional networks? Do you want to use software-based networks? Everything we've been doing classically, we can bring across into the space, okay? I'm not saying what the solution is, okay? What I'm saying is we need to think about it. We need to think about this as part of our stack. So I want to be provocative in a sense. We need to think about, normally when we think about routing and various things like this, this is a classical concept. Does quantum mechanics allow us to do anything different? So when I think about a classical packet, okay, the classical packet goes to you. But actually, if it's quantum, why can't I send part of it via you, part of it via David to you in a coherent superposition? Is that a packet? How do I route this information? How does this stuff kind of work? I mean, there are these possibilities there that I don't think we even know how to ask the questions properly in a sense. What do I think about a packet as just part of the quantum state that you get, and David has another packet, okay? And then at the end, I combine the packets. So I'm behaving more classically in a sense. It's not clear actually how we consider this, because we can't just say, oh, we'll do it as we do classically, because quantum mechanics gives us something more. But really, part of what I want to say is that we really do need to start thinking about quantum routing, network aggregation, and various concepts like this. I think Rod had the slide up as old work of the Rod as well. So I have 5 different paths to you, okay? Which one do I choose? Knowing me, I'm just going to flip a coin, okay? But what I'm saying is, classically, there are a number of algorithms that allow us to do this. What we found is that a lot of the classical infrastructure, Dijkstra's algorithm that comes across, we can use it in the quantum mechanical world, okay? Is it absolutely guaranteed to be the best? Don't know. But we've got that, we can bring that functionality across. And this is kind of work that we've done with Rod in a sense. To say if you have the different paths, how do you choose them in a sense? What are the metrics for choosing them? What are the metrics? So if I want to choose a path, what constraints am I going to give you? Do I need to start thinking about, is Nico in the background? Yep. We need to start thinking about quality of service and various things like this. There's a whole series of things we've had in the classical world that we need to move into the quantum world to just start to see, to allow this to make informed decisions on actually how we move information around. But I want to get to something either much simpler or much harder, okay? And Jackie had some of this in hers, and this is, she called it hyperentanglement. We've been using for a long time the word quantum multiplexing because we were having multiple degrees of freedom on one photon, okay? And the very old polarization and spatial stuff from Jackie. Some work we did a few years ago on creating cluster states with time and frequency together. Non-commuting, normally you would never want to use non-commuting observables to encode information, okay? That seems very bad thing to do, okay? But as long as you make sure that the overlap between them is not too bad, you can encode in time and frequency. We do this in the classical world. And this one photon experiment we had here, a 2-photon experiment, 2 photons, a total of an 81-dimensional Hilbert space. Each 2 degrees of freedom, 3 time bins, 3 frequency bins, so 9 degrees on Alice, 9 degrees on Bob, 81 all over compared to 4, okay? That seems quite nice. So does multiplexing actually help in a sense? Why would you want to add complexity, okay? And this is some work from Nico, who's in the background. Nico, you should present this rather than me. But the idea was, does multiplexing actually help? And the simple task that we decided we wanted to think about here in a sense, okay, Alice and Bob have 2 memories each. I want to create 2 bell pairs between the 2 of them, okay? If the probability of sending a photon through each of them is P, what's the best strategy for making sure that both have both pairs? And what you could do is you could just try and send a single photon between 2 of them and just wait until both succeed. Or you could take a single photon, entangle that single photon with a quantum memory, move the information in the photon to a different degree of freedom, entangle it with the second photon, shove the photon over the channel, entangle one of the degrees of freedom with that photon here, move back to the original encoding, entangle the photon part with the second memory, so you can end up with entanglement. You'd end up with 2 entangled states using only 1 photon. And the extra elements you need in your circuit are quantum switches, okay? So the question is, which is cheaper? And if you want to look at success probabilities, which one do you do? It depends really on what's your memory lifetime, okay? Multiplexing, as long as the memories, if you don't have perfect memories, there's a nice window where multiplexing actually works, okay? But we can actually go further than this. Because I want to live in the communication space, okay? What I'm going to tell you now is, okay, we can generate 2 pairs, okay, of fidelity F. They're not good enough. Please do purification. Okay? That means I've then got to do C0 gates and various things like this, okay? But given I've got the one photon going across carrying both degrees of freedom, can I do more here? So what we can think about doing is taking half of the circuit, okay? Still doing what Alice does, that becomes unchanged. But when we send the photon over to Bob, we're going to do the purification step while it's still in the photon. You say, oh, gates and photons, yeah. On the same degree of freedom, in the same photon, 2 different degrees of freedom are easy. Doing a C0 gate between polarization and time bin is an easy operation. It's not probabilistic. It may depend on how good your switches are, but I can do that. So I can do the C0 gate in here, and then just then bring the result out onto my memory here. So while I still need to do a C0 over here, I can do entanglement distribution and purification in one time step, where not only do I save 1 photon, I also save 1 memory. Multiplexing has some advantages. Hyperentanglement quantum multiplexing. I mean, I've been harping on this a lot since I've been here. Use the resources you want. Use the resources that you have as efficiently as you can. So if you've got a photon, don't restrict yourself to just using the most trivial degree of freedom or the thing that's easiest. Because basically at the moment, photons are precious. Yeah, Jackie said photons, there's many of them, okay? But still, in the classical world, I pack as much information as I can. And I want to do the same here. So this was just a simple example that we thought up a while ago. So I could send 6 qubits, okay? This is putting into an error correction code. So I could send 6 qubits, means I send 6 photons, okay? And I lose some of those photons. But what happens is that I could take these 6 qubits and encode them on 3 photons. I lose 1 photon, I can still recover the information. So by using more degrees of freedom, if I lose a photon, I can recover. I think I'm going to skip this maths because it's in the notes, because that was a lot of maths. The key though is when you start thinking about hyperentanglement and various things like this, and you move from purification to error correction, we can start saving both memories and photons. And we can make it more resilient to loss. So basically I say we save photons, therefore I can operate at a point where I have slightly more photon loss and I still beat the case where I send 2 individual photons or multiple individual photons. I mean, when I start thinking about, and this is a complicated diagram, okay? I keep talking about error correction codes and I keep thinking of qubits. Why? Because I've been thinking in computation too much. In the classical world, we had to read Solomon codes. In the quantum world, I can start thinking about qubits, and qubits are a nice hot topic at the moment where people say, oh yeah, use 0, 1, 2, okay? They're more robust to noise and various things like this. The interesting thing is a lot of this qubit space started about 2000, okay? On an island, smaller island than we have here, unfortunately, on Heron Island in Australia, where you could where it was roughly 7 minutes to run around the outside of the island. But a lot of our physics was done on a table with napkins, and there we worked out some of how the volume, it wasn't cast in terms of how robust qubits were, but we found out that if you thought about a qubit, a general 2-qubit state, there's a small area inside where it's a separable states. When we thought about these bigger spheres in terms of qubits, we found out the relative proportion of separable states was smaller. Therefore, in a sense, they were more resilient to noise and various things like this. So in qubits, the qubit encodings allow us a lot of power. And what I wanted to show here was this is a transmission probability. And depending on whether you encode 5 qubits per photon or you encode 1, the scales are off the planet in a sense, okay? This blue line, so Nico, what's it get up to 5,000 or something? At 0.8, it's really, you require huge numbers of resource. But by doing this hyperentanglement, this multiplexing, the 5 qubits or 5 qubits per photon, we can still maintain modest resources in a sense. Do people use qubits for anything? Yes. qubits, multiplexing that is used in QKD at the moment. Typically, and I'm being very cheeky here, okay? Multiplexing requires only optical switches. I'm being cheeky because I want low loss, fast optical switches. I want to switch at less than 0.1 dB at 100 picoseconds, please. Actually, the technology is coming. So basically, in the photonics world, computation world, we've had to do this. So some of the work from the photonic quantum computing companies are building switches of this form. We're not using it for communication. It's not being used in communication, but we need that when we want to route cluster states together and events. We need these kind of switches. So when I say extra, I'm just being a little bit cheeky. Question? Has anyone used this kind of multiplexing concept to do anything not QKD related in a sense? An experiment that I was involved with that was with Joey Pan's group and Anton Zeilinger. Very simple experiment, okay? I want to take a physical qubit and teleport it into a logical state. So I want to encode the information and kind of show that we're slightly more resilient. By encoding it, the state is more resilient. I'm glad I'm a theorist. A 12-qubit photonics experiment, but only 6 photons because we use hyperentanglement. And so what we can do is use one parametric source to herald a photon coming out. Use 4 more to basically build a logical state. Bell state measurement, effective teleportation, and we can move the information that we encode on this photon across into this logically encoded photon and show that it was more resilient to the noise process. I can talk to people more afterwards, but I mean, these things that kind of can be done. If I want to do a 12 photon experiment, it's probably possible, okay? It's probably possible, but I'm not sure whether the 12-fold coincidence rates are more than a few photons per day. Aggregation. When you think about networking and that there's almost never one single path between any two parties. So on campus, you'll come up to campus on Thursday. We have the campus, the main area of campus is kind of an oval or a circle in a sense. So you would think, okay, if I build a network, I can just go around, okay? But as a network engineer, we made sure there were two separate paths so that one of them goes down, we have another path to get information. So if you have multiple paths, classically, I just choose one of them that I want to use. Quantum mechanically, what do I do? Do I just choose one? Do I choose them all? That's kind of the fundamental. So classically, this time I use this one. Next time I use this one. This one has a gremlin on it, my favorite gremlin. What do I do quantum mechanically? Quantum mechanically, I'm really afraid of this person. They're going to take my data. So what quantum aggregation allows us to start doing is to take multiple of these paths and aggregate them into a new virtual pipe, okay? So it looks like information is being sent collectively across these, but there's many different paths. And this is primarily work from Nico. So what we had is we just considered two paths in this case. And we had the transmission probability through one path, the transmission probability through the second path. And so what you could do is you could think about if you're doing these in error correction codes, the transmission paths don't even have to have the same success probabilities, transmission probabilities. You could take, and if you're using multiple ones, so you've got the two paths, you can use some stronger ones and multiple fibers and one path, a few in the other. You could actually compensate if there's not enough fibers in the main path, taking a few weak ones from that other path. You can combine them and still transmit information more reliably than you could if you without it. So actually, aggregation is really, really interesting in that sense, because it forces you the question as to how do you want to allocate resources? Greedy? Who has the most money? Gets the best? Do you equally share them out? There's a series of choices that I kind of like the idea that even the network, and it kind of will probably surprise you, having a few peers that even a bad quality where the probability of success of getting it through the link is only 10%, they can still be useful in the overall aggregation scheme. I can't have too many of them, but a few of them can allow me to get the information through at the quality that I want. Now, what if these things don't have the same path lengths? So there has to be a memory or delay in one case. You can start working out trade-offs and various things like this. So you start with short plus long, one short plus two long, three long. How do you do things? There's a whole series of fundamental questions when we start thinking about these networks that we're just opening the door to see what makes sense. The challenge for the younger generation, I phrase this. And I can probably say, I have the whitest hair of anyone here in the room, so it's a challenge I can give. I want this. I want the quantum internet. I want quantum cloud computing, preferably before I retire, okay? You have 10 years, okay? But the question that we're discussing with the number of you and the copy break and various things like this is I can't just give you a challenge and say, build that. we really do need to start thinking about how do I move from what we have now to this global quantum internet. And so that we need to start thinking about concepts like edge computing, which probably most of you have never heard about, in a sense. It's not something we teach networking. It's not something we teach physicists. But it's an old concept that's come back into importance now. If I think about a network, and I'm at the edge of the network, typically at the edge of the network, you have nothing. So maybe at the edge of maybe if you're sitting on main campus, I give you, from here to Tokyo, I'm going to give you 120 gigabit link to Tokyo, okay? From the main campus to here, I'm going to give David a gigabit link, okay? David, who's transmitting down to the beach, is going to give the user down there, should we be generous? Kilobits. And unreliable. So when David closes the screen, you lose the connection, okay? So what we need to think about is, but maybe I'm the person sitting on the beach and I really want that link to be able to give this presentation, okay? So the whole point about edge computing is starting to think about what resources can I put at the edge of a network where communication is potentially limited in there, and then connect them together. So, I mean, the typical ones that people talk about is maybe you have some small scale quantum processors, okay? But then you can add some quantum sensors, quantum clocks and various things like this, and you can just connect these things together over a few K. What we hope is, in terms of the communications aspect, okay, I'm not doing purification. I'm hoping that everything I can do is just entanglement distribution, single photons, or various things like this, that I do not need to do anything complicated. But it may not be point to point, okay? So this person here does not have a direct connection between the sensor. So when we think about this in the quantum regime, maybe I have a lot of classical communication, but yes, my quantum resources in terms of communication are very limited, but I have these good devices. So we can start building these things up. And then once I have this, I can start connecting a few of these together and building larger scale networks. So what may happen in here is I'm poor, okay? OIST is poor. I only have a small quantum computer, okay? They only gave me a phone rather than a Mac Mini. But what can happen is that David here in the middle has a bigger computer. So the concept of cloud computing, if my phone is enough to do what I want, I use my phone. If I can't, then in edge computing, I push the data through the network connections I have to David. Let's say David's computer is not big enough. It is a bit small. Then I can push it up into the cloud and send it to an HPC. At the same time, what we're doing along every step is we're saving resources. We're saving quantum resources that we need to send. Where do you really see edge computing? The Internet of Things is a very, very common example. We have all these little electronic appliances sitting around. They tend to connect to local networks. Whoops, that's me. They tend to connect to local devices, local networks, rather than connecting to the internet in a sense. So quantum, I'm going to have sensors, computers. Alice may not have a quantum computer, but she can access one in a sense. But if we're going to start thinking about these concepts of edge computing, I'm going to have to think about moving data around. okay? And one of the simplest algorithm problems going back 30 years, whoops. Alice and Bob, Bill and David have two quantum states. You have a quantum computer. I don't know, is my state the same as David's? David wants to know the same. How do we answer this question in a sense, okay? I could send my state to David, okay? I'm not sure I'll get it back. So, I mean, it is called the control swap test. There's many names for it. It's a very old, it's one of the earliest algorithms, it's one of the earliest algorithms. If everything's local, if everything is with me in here, we can just plug in and we can do this. We're now on a network. What do we do? Two scenarios come to mind, okay? First thing I could do is I have my two states within my quantum computer, okay? I now have two ancilla photons. I do a control, I do a swap gate to you. David does a swap gate to you. You can now do the swap test, okay, locally yourself. That requires me and you establishing having a control swap gate, or swap gate. You and David having a swap gate. That sounds plausible, that may be possible. Alternatively, we could just share a bell pair. You can share a bell pair with David. Then I can just teleport you the state. Which do you use? Okay. Do you use remote gates or teleportation? Is teleportation just equivalent? Can I do remote gates with just one bell pair? Which one is more friendly in terms of information resources? Think about the control swap gate. If I give you standard gates, C knots, or various things like this, to do a swap gate, even if we're very kind, okay, and we know that in your quantum computer, you initialize your state to 0, to do the minimalist swap gate requires you have to do two C knot gates. Yeah. So this requires at least two C knot gates, two bell pairs, something like this. So this is actually using more resources than just doing the teleportation. So if my network is really constrained, I really have to think about how I use these resources in the most efficient way. Normally, what I'm saying, and this is a surprise to me, I'm happy to do teleportation and use the free classical messaging. So in this case, I do quantum, and here I supplement my limited quantum with classical knowledge, and that's kind of why it works. You can think this doesn't make much difference, okay? But actually, if we really are constrained in terms of the resources of various things like this, it makes a difference. What I can also always do as well, okay? And this was kind of a funny experiment we did a while ago. What was the date on this? Did I put a date somewhere? I think about 2000, okay? I should update with this with a slide, okay? So what we wanted to do is we had a quantum computer. I wanted to generate a complicated state. And I know my states. I'm going to give one of you an ergodic state of matter on 63 qubits, or maybe I give you a localized state of matter. And I want you to tell me which one it is. So the question we started thinking about in terms of network processing power and various things like this is we could bring this through a circuit and get the solution out by only measuring 1 qubit and then sending this classical information down to an HPC to process to bring the data back up. So I can start thinking about minimizing quantum resources to really make these kind of measurements, the amount of information I need to send across the network, either 1 qubit or even classical, okay? And so what this means is I'm trying to sense something, you can actually start seeing some advantages. Given time is marching on, and some design considerations, I think, for networks. Number one principle, if you want to build a quantum network, and it's likely to be complex, think about how you build your classical communications network at the same time. Don't assume someone else is just going to give it to you, okay? First point. Second point, don't assume that two parties know where they are or how to talk to one another directly. Even if I'm trying to ring David on my cell phone and on David's cell phone, I have no idea where on the network David is. And you may say it's simple, okay? The phone call is just going to go to the local machine and come between this, but no. Maybe David's on Docomo and I'm on AU, and this has to go through some substation in Naha to connect our two networks together, okay? So the second point, okay, it's an important design consideration that you have to think about to start. No surprise, first generation quantum repeaters are slow. Live with it. Slow doesn't mean not useful. Slow means that within certain constraints, they'll have applications. The high generation quantum repeater approaches now allow you to do both distribution of entanglement, but they also allow direct transmission. No longer do we have to get to the stage where communication is done by establishing a bell pair. Bad design. No longer do we, oops. Sorry about that. So no longer, is it still working? Yeah. So yeah, sorry about that. So the key is that the third generation quantum repeaters allow you to distribute entanglement, but they also allow you to just directly transmit signals, quantum signals. That direct transmission of quantum signals is much more like what we do in the classical world. What's the problem with that? Security. Third generation repeaters in direct transmission mode have no security built into it, but they're fast, okay? So third generation repeaters, we have to just be very, very careful with what the design considerations are. Yes. You chose the right workshop to come to because here's the provocative statement to finish. In my first slide, or first few slides, I talked about the second quantum technology revolution coined by John Dowling and Jared Milburn. And they talked about the power of quantum sensors, the power of quantum computers. They were good. They talked a little bit about communication, but I'm going to be provocative. If you want this quantum power, build your network.
we cannot really fully explain the power of quantum technologies without a network to put them on. And you may say, he's joking. Actually, how many electronic devices do you have with you? Yeah, David's watch. Everything at the moment, we've moved into a society where I don't have it, but a number of my neighbors' fridges talk to the internet to tell them that they need to buy milk, okay? So this Internet of Things, okay, means that we're getting more and more devices connected to everyone. When these become more and more quantum devices, we're going to need a communication channel to do this. So the statement I'm saying is quantum communication is the key enabler to fully realize the potential the second quantum revolution gives. Ignore quantum communication and you're hamstringing yourself. You won't succeed. We will not be able to build quantum data centers. We will not be able to synchronize clocks arbitrarily and various things like this. You need this. And I think that's a good time to finish because we have an hour to lunch. Beach time.
Slide 151, you actually mentioned
Okay.
quantum neural networks.
Let me find slide 131.
151. And not 150, 51.
151 or?
Yeah, 51.
That is slide 131.
151.
151.
Yeah. So I didn't get the point because in neural networks, usually at the end, there is only one neuron. So they are just normal neural network. So how is it like related to fog computing and how is related to sensing?
So the whole point in this particular case when we did it was you're given a state of matter, okay? So the question we've got to do is to say, and you've got to tell me, you've got the state of matter. A sensor gives you this. I need to take that state, and then check: is it ergodic or localized? The way we do it at the moment typically is I will go through and measure every qubit. Okay. What's the problem measuring every qubit? Superconducting processor, 63 qubits, 97% detection accuracy, 0.97 to the power of 63 is 1%, less than 1%. So I can't do it. So the whole point though is I can start taking that state, put it through a quantum processor, and measure the result out on 1 qubit.
So this blue gate is the entangling gate?
This here at the moment is just the way of creating the sensor state, yes. And this is the way that we send it to a quantum computer to measure it in a sense. So this part here could be over a communications channel if you wanted. This could be in a small scale quantum computer in a sense. And then we need, we can take it out of that and then we send it on a classical channel to a neural network, update it, send it back in, and then we iterate it. But it is kind of surprising that this works by just measuring 1 qubit. And people ask why. I only asked a binary question. I was very cheeky when I asked the question. I said, is it ergodic or localized? I lied to you. Is it ergodic or not ergodic? I'm only giving you an ergodic or localized state, but my question really is a binary question, ergodic or not ergodic? Given that's a binary question, I can read that on a 1 qubit, correct? Down means ergodic, up means not ergodic. So we can condense all that matter, all that information into one qubit. And it's really, really effective. It was surprising how effective this was. And it worked on 63 qubits. When we tried to do just measure the populations of every qubits, we had a problem. My experimental colleagues did not want to do tomography because tomography would be too expensive. But I mean, we could take some of these edge ideas and talk about a sensor part, then talk about a small scale quantum computer, take the information out of the quantum computer into another network appliance, process, bring things back. And this kind of works very well, really limiting the amount of communication that we require in a sense. That's a toy experiment, but it's kind of saying, one of the things is, think about your design, think about really what you're trying to do. And then once you think, we quite often in a lot of experiments in photonics, our default is that we measure every qubit. We do full tomography, okay? We're going to get to the stage very quickly when I have a 20 photon machine, okay? Good luck. I came from the generation where 2 qubit tomography was nice, okay? 20 qubit tomography you can't do. So therefore so what people have moved is from doing full tomography on multiple qubits. Now we're doing entangled witnesses, and we're doing witnesses for certain things. But the witnesses are also giving us more information than we want. Typically in the process, I want a yes, no answer typically. If you want a yes, no answer question, you can start designing these systems intelligently to allow you to do it. Yeah, we can chat over lunch. That's it for the day. Thank you. Lunch in 1 hour.